Every year, the world generates more than 2 billion tons of waste, enough to pile up into mountains that leave thousands of cities running out of landfill space. But in Sweden, the story takes the opposite direction. The country's waste-to-energy and district heating network is so well developed that its plants receive more than 1 million tons of waste from other European countries every year. Even more surprisingly, the countries sending that waste actually pay Sweden to process it. What the rest of the world is trying to throw away has become a commodity that Sweden gets paid to receive. So how is that waste transformed inside these plants into electricity and heat capable of warming an entire city? Nearly 40% of the world's waste is still dumped in open landfills with little or no control. In many African cities, that figure can reach as high as 90%. These massive dumps take up valuable land, leak hazardous chemicals into the environment, and release methane, a greenhouse gas that traps heat far more effectively than carbon dioxide. For decades, landfilling was humanity's default way of dealing with waste. But as available land became scarce and pollution grew increasingly difficult to ignore, some countries chose a different path: burning waste to generate electricity and heat. This is known as waste-to-energy, a technology that converts waste into usable energy. But not everything we throw away can simply be fed into an incinerator. In this video, we'll take an in-depth look at the world's most widely used waste-to-energy technology: mass burn, where most municipal solid waste remaining after collection is fed directly into the furnace without the complex mechanical pre-treatment required by many other technologies. Everything begins when a garbage truck is weighed before unloading its entire load into a waste bunker about 20 to 30 meters deep, roughly the height of an 8-story building. From a control room overlooking the bunker, a giant overhead crane continuously mixes the waste to create a more consistent fuel for combustion, while drawing air from the bunker into the furnace to help contain unpleasant odors. Once the waste has been thoroughly mixed, the crane feeds it into the furnace, where temperatures range from 850 to 1,450 degrees Celsius. The waste moves slowly across a mechanical moving grate through the combustion zone, allowing it to burn completely rather than simply becoming charred on the surface, until all that remains is ash. The heat generated inside the furnace boils water in the boiler, producing high-pressure steam. That steam is then directed through a turbine, causing it to spin a generator and produce electricity. Just a few seconds earlier, it was nothing more than trash. Now, it has become electricity flowing directly into the national power grid. But electricity is not the only thing produced during this process. Before leaving the smokestack, the hot flue gas passes through multiple cleaning stages. Activated carbon captures dioxins and mercury, chemicals neutralize acidic gases, and filtration systems remove fine particulate matter. At the bottom of the furnace, the heavier bottom ash is collected, while any remaining metals are recovered for recycling. The lighter fly ash captured by the air pollution control system contains much higher concentrations of contaminants and must be handled as hazardous waste. By the time the emissions leave the stack, they are almost invisible. Yet that very fact has made waste-to-energy one of the most controversial technologies in modern environmental management. So, what kinds of waste can actually be turned into electricity, and what kinds cannot? Dirty paper, mixed plastics that cannot be recycled, textiles, wood, rubber, and organic waste are the main types of fuel used in waste-to-energy plants. Although wet organic waste produces much less energy because of its high moisture content. Metals and glass are different. They do not burn, generate virtually no energy, and can be recycled almost indefinitely without losing quality. That is why they are usually separated from the waste stream, either before or after incineration. This is also why no one burns 100% of the waste. Burning recyclable materials wastes valuable resources, while overly wet organic waste is often better suited for composting or anaerobic digestion. Another group of materials must be handled separately altogether. First are lithium batteries, which can explode inside garbage trucks and start fires. Second is electronic waste, which contains hazardous heavy metals. Third is hazardous medical waste, which requires much higher temperatures for safe sterilization. Finally, there is PVC plastic. Although some modern facilities are capable of burning it, its high chlorine content makes flue gas treatment far more challenging. For the waste that is truly suitable for incineration, its energy value is greater than most people realize. 1 ton of municipal waste can generate roughly 550 kilowatt-hours of electricity, enough to power an average American household for nearly 3 weeks. Now let's go back to the question we asked at the beginning of this video. Why does Sweden import waste? Long, cold winters led the country to build an extensive district heating network decades ago. Waste-to-energy plants not only generate electricity, but also supply heat to that network, allowing them to utilize up to about 85% of the energy contained in the waste, far more than conventional plants that generate electricity alone. At the same time, high landfill taxes have pushed more waste toward energy recovery instead of disposal. But that very success has created an unexpected problem. Sweden's waste-to-energy capacity exceeds the amount of suitable domestic waste available, forcing the country to import anywhere from hundreds of thousands to more than 1 million tons of waste from across Europe each year. As a result, about half of all homes in Sweden are heated through district heating systems, with waste-to-energy serving as one of their major heat sources. Only about 4% of the country's waste ends up in landfills. But don't assume Sweden has run out of waste simply because it recycles so well. Roughly half of its municipal solid waste is still sent directly to waste-to-energy plants, and the fossil-based plastics within that waste continue to release carbon dioxide when burned. Waste-to-energy can significantly reduce the need for landfills, but it does not eliminate the challenge of greenhouse gas emissions. If Sweden represents a carefully engineered national system, the next 2 plants showcase 2 very different approaches to the same technology. In Copenhagen, instead of hiding a waste-to-energy plant on the outskirts of the city, engineers placed it right in the urban center and transformed its roof into an artificial ski slope. Amager Bakke processes more than 400,000 tons of waste every year and supplies heat to around 140,000 households. But don't let the ski slope fool you. Beneath it lies the same industrial reality found in any other waste-to-energy facility: a massive incinerator and a sophisticated flue gas cleaning system. In Shenzhen, the story is all about scale. The Shenzhen East Waste-to-Energy plant burns up to 5,000 tons of waste every day, processing roughly 1/3 of the city's municipal waste. China now operates hundreds of waste-to-energy plants, giving it the largest installed waste-to-energy capacity in the world. One approach transforms industrial infrastructure into public space. The other scales it up to industrial proportions to tackle the enormous waste challenge of a megacity. If waste-to-energy is so effective, why hasn't the United States, one of the world's largest economies, built as many waste-to-energy plants as Europe? The answer comes down to 4 key factors working together. First, in much of the United States, landfilling is still far cheaper than incineration because the country has abundant land available for disposal. Second, unlike Northern Europe, most parts of the U.S. do not have extensive district heating networks. As a result, waste-to-energy plants can sell electricity but not heat, significantly reducing their overall economic efficiency. Third, building a waste-to-energy plant requires a massive upfront investment, along with long-term waste supply contracts to ensure the facility can operate reliably for decades. And fourth, many American communities continue to oppose new waste-to-energy plants because of concerns about air pollution, concerns rooted in the legacy of older incinerators that caused severe emissions before the Clean Air Act was enacted in 1970. As a result, the United States today has only about 60 to 75 waste-to-energy plants, and that number has gradually declined over time. Meanwhile, Europe operates more than 490 such facilities. Waste does not simply disappear. Most of it is transformed into flue gas, heat, and electricity, while the rest remains in the ash and the pollutants that have been captured. From Sweden importing waste, to Copenhagen turning a power plant into a public attraction, to Shenzhen burning thousands of tons of waste every day, they are all trying to answer the same question. How do we deal with something humanity never stops producing? But waste-to-energy is not the ultimate solution. It can reduce the amount of waste sent to landfills, but it cannot replace the need for people to generate less waste in the first place. And as global waste continues to grow faster than facilities like these can be built, the real question is no longer how efficiently we burn our waste, but whether humanity will ever stop producing so much of it.